Okie dokie, everybody. Chapter 12, Metabolism of Other Sugars and Pentose Phosphate Pathway. We'll call this PPP. So the objectives are draw the reactions demonstrating how fructose, galactose, and mannose are transformed into glycolytic intermediates. State the defective enzymes in hereditary fructose intolerance, essential fructosuria, classical galactosemia, and non-classical galactosemia. State the clinical significance of the above disorders. Describe the pentose phosphate pathway and understand the metabolic significance of the oxidative and non-oxidative phase of the pentose phosphate pathway. Okay, so talking about metabolism of hexoses other than glucose. Real quick, remember hexo meaning 6. Os is referring to sugar, so we're talking about 6 carbon sugars right now. Just like glucose is a 6 carbon sugar, the rest of these also have 6 carbons. They're just slightly different makeup. 3 important hexoses besides glucose are fructose, galactose, and mannose. These are also major sources of cellular energy. Fructose metabolism. So many fruits contain sucrose and fructose. So sucrose is broken down to glucose and fructose. Keep track of these little equations of the different sugars of our, remember if we have a 2 sugar molecule, what is that called? That is our disaccharide versus each of our individuals are our monosaccharides like glucose and fructose. Okay, so sucrose breaks down into glucose and fructose. Glucose goes off and it can do its thing, but fructose is not quite in the exact same position as glucose was. We can see that while glucose has more of this hexagon structure and just 1 carbon, the 6 carbon popping off, fructose has 4 carbons and has more of a 5 one was 1, 2, 3, 4, 5. We have a pentagram shape with 2 of our carbons popping up off the edges. So we need to do a little bit of changing of that in order to change it into what we need to do. So we can have, so in the metabolism of fructose, we have a couple of different options, right? We can, using the enzyme hexokinase and ATP, we can convert that fructose into fructose 6-phosphate. If we recognize fructose 6-phosphate is one of our already occurring intermediates of glycolysis, and that can immediately just be plugged right into glycolysis down the line rather than going from glucose and then changing into the fructose 6-phosphate. It's just going to go directly into the system at that stage. Now, we can also have fructokinase act on it and give us fructose 1-phosphate. So this fructose 1-phosphate we call this the open chain form. So where this is all bunched up together. This is now like the free kind of forming chain. And that can be converted by fructose 1-phosphate aldolase to a glyceraldehyde. And we remember glyceraldehyde is another one that is in glycolysis. Convert glyceraldehyde to glyceraldehyde 3-phosphate, and glyceraldehyde 3-phosphate then plugs right back again into glycolysis. We can also from glyceraldehyde go to form glycerol 3-phosphate, dihydroxyacetone phosphate. If we look at this, all here these steps, that's glycerol 3-phosphate, dihydroxyacetone phosphate. Where have we seen those before? Last chapter we were talking about these, thinking about the shuttles. Remember the exact name of it is space. I'm spacing on the exact name right now. Let's just quick slide up and see there it is, the glycerophosphate shuttle. So there we see our dihydroxyacetone phosphate, our glycerol 3-phosphate. And that can also be converted from glycerol 3-phosphate into the dihydroxyacetone phosphate, which can actually then be converted to the glyceraldehyde 3-phosphate and be plugged right into glycolysis. So we can see this is just showing us the different ways that fructose can be used in order to get to glycolysis. Another one that we can see right here is lipid synthesis, so fat synthesis. So glycerol, a little bit more next try, we'll talk more about fat synthesis. But when we talk about fat synthesis, triglycerides. So triglycerides, we have a glycerol backbone, and we actually will then have three triglycerides coming off, or we will have three fatty acid chains attached to that glycerol, and that forms our triglycerides, which is our fat storage and the way that we transport some of our fats. Sweet. And this will be more Biochem 2. Next trimester, we'll get into a lot of the cholesterol and the fat type stuff. So fructose metabolism. In the muscle, the fructose can be phosphorylated by hexokinase to fructose 6-phosphate. So it's just going straight in. In the liver, the glucokinase can't phosphorylate fructose. So fructose is going to mostly be used by the muscle. Kind of curious. This is a question that I sort of have. I wonder if this is why eating fruit or high fructose foods give good energy before working out. We'll take a look at that later and see. This is what's kind of fun, where you can start to look at the application of these things. Don't just sit here and go through the material and just be like, whatever, it's biochemistry. Try and find out and apply these things to your real life and see what you can apply and maybe what's important and maybe what's cool. Okay, so in the liver, the fructose forms, this is the fructose 1-phosphate by a fructokinase. So this is where our separation is that we can see. So here we have, this is happening in the muscle, and this is all, actually you can see it up here, all of this happens in the liver. This is in the muscle versus the liver. So the muscle, very simple. The liver, a whole bunch of stuff can happen. In the liver, the fructose forms the fructose 1-phosphate by fructokinase. The F1P forms dihydroxyacetone phosphate and glyceraldehyde by FR1P aldolase. Then glyceraldehyde 3-phosphate is produced by the action of glyceraldehyde kinase and triose phosphate isomerase. Glyceraldehyde 3-phosphate enters into the glycolytic pathway. In some conditions of excess carbohydrate or fructose, glyceraldehyde can be converted to glycerol. This is what we're talking about. Excess carbohydrates or fructose, glyceraldehyde can be converted to glycerol. So this is when we have lots of extra carbs and lots of extra sugar in our blood that we're going to have turn into fat storage, leading to lipid synthesis. In condition of energy demand, glycerol kinase can phosphorylate glycerol to glycerol 3-phosphate, oxidize it to form dihydroxyacetone phosphate by dehydrogenase, catalyze the reaction, then to glyceraldehyde 3-phosphate that enters into glycolysis. All this is just all of the words of what we just walked through this beautiful chart. Now onto galactose. Galactose is a C4 epimer of glucose, and galactose is a milk sugar and the product of hydrolysis of lactose. It is metabolized in the liver, and it requires 4 reactions to enter into glycolysis. So here we have the metabolism of galactose. Galactose, we have galactokinase to galactose 1-phosphate. And we'll have a little bit of a process here with the UDP galactose being converted to UDP glucose. And that gets us to glucose 1-phosphate. And glucose 1-phosphate can be changed to glucose 6-phosphate. And that can enter into glycolysis. The big differentiating factor we're going to be looking for in test questions is right here. These UDP is going to be our bigger focus, kind of what makes this process much different or easier to recognize compared to the others. So the galactose forms galactose 1-phosphate by galactokinase, right there. Galactose 1P receives UDP from UDP glucose and forms UDP galactose, and glucose 1-phosphate by galactose 1P uridylyl transferase. Glucose 1P is converted to glucose 6P by phosphoglucomutase. G6P enters the glycolysis pathway. And then this is, again, just repeating exactly what we saw up in here in this chart. This whole processes, there isn't a lot of, I would say, memorization or understanding in these ones. I think the more important thing in all of this is to just do those keyword recognition and recognize the enzymes, recognize the general flow, and the words that tend to be different or specific to these specific pathways, and that will help you a lot on your exam when taking these, when getting questions about these pathways or these metabolisms. So mannose is a C2 epimer of glucose. Again, meaning that we look at the C2 carbon, meaning that the C2 carbon is different. See how this is flipped? So how galactose was a C4. All this is the same. 1, 2, 3. Sorry, this one right here. 1, 2, 3, 4. This guy right here, how they're flipped. That's the C4 epimer. Mannose is the C2 epimer. Here we have the mannose with the hexokinase, phosphorylates it, and then we have a phosphomannose isomerase, which is going to rearrange it to get us to fructose 6-phosphate, which then goes easily into glycolysis. Okay, so just look over those. Remember, check out those, where these are happening, whether it's the muscle or in the liver, and what the enzymes are, and some of the general. I remember mannose goes to fructose 6-phosphate in order to enter glycolysis, and that one, mannose is pretty simple. Okay, now the pentose phosphate pathway. This is one that's a little bit more touched on. That we honestly didn't need to remember a lot of the metabolism up above, but the pentose phosphate pathway is a little bit more important, and you will get quite a few questions on this sort of material. So, an alternative pathway to metabolize glucose is accomplished by pentose phosphate pathway, or PPP. PPP does not oxidize glucose via glucose 6-phosphate to produce ATP. Instead, this pathway produces specialized products, such as NADPH, required for numerous reductive biosynthetic pathways, and provide pentoses for nucleic acid biosynthesis, including production of other monosaccharides such as ribulose, xylulose, erythrose, fructose, acetoheptulose, glyceraldehyde, etc. Is required for the synthesis of other important biomolecules in humans. I'm going to need to pause recording real quick to hear something. I'll be right back.